Today we are going to do section 1.3. But before that, let's look at some homework that I have found and ask yourself this question: can you do this? Now, if this stuff looks pretty good to you, and you can do it in your sleep, okay, you know all the rules about what these things are and how to manipulate them, then you can skip this section. You don't even have to do that, just as long as you're sure that you know how. If you are only about 90% sure, then let's go through the chapter and then become 100% sure of what's going on. Now let's begin on section 1.3 on page 39. First, let's on the page you see a right angle triangle, and it mentions something called the Pythagoras theorem, okay, which states that a squared plus b squared equal to c squared. Now you absolutely must memorize the Pythagoras theorem if you haven't done so already. That's referring to the relationship of the lengths, okay? The two sides are called, the perpendicular sides are called A and B, and the slanted side, the longest side, is called C. They have a relationship of a squared plus b squared equal to c squared. In fact, from this point on, in your whole life, every time you see a right angle triangle, you must immediately remember the Pythagoras theorem for no reason whatsoever. Okay, that's how important this theorem is. The Pythagoras theorem is the ultimate, the most important theorem of all math through high school. Okay, and it will be used constantly. So do not forget the Pythagoras theorem. That's one thing you must memorize, and that is, in a right angled triangle, a squared plus b squared equals to c squared. All right, so now that we have said that, how do you, to calculate then the c a lot of times, then or a and b when you're giving the other two sides, then you have to figure out what the square root is, okay? Like this example right here. We have on the example in your book, we have this situation where c squared is equal to end up being, if you calculate what a squared and b squared is, then you figure that c squared is 169, which is the square of 13. Then you have to calculate that, then you take something called the square root. The square root is this. Now, the reason this section is called the radicals is because the square root symbol is called a radical, but that's of no real significance, so we'll just move on. Okay, let's look at example 1. Now let's go to page 40 and look at example 1. But before that, look at the line right before page 40, where it says the square root of 25 equal to plus or minus 5. It does. However, in this particular way we write it, if we write the radical sign, the square root, we only refer to the positive one. That is, if we want to refer to the negative one, we'll write a negative sign in front of it, just to be clear, okay, so that there's no confusion. So generally speaking, the radical sign refers to the positive root only, even though we know in the back of our head that the square root can be positive or negative. So let's look at the example 1 and say you look at part A. Right? In fact, let's look at part B. Okay, you have the square root of 6, and then it has two square roots. What do you do when you have two? Well, you do one at a time. The square root of 16 is 4, and then the square root of 4 is 2. And so that's how you do that. So please do example 1 as part of your homework. The next, look down at the bottom of the page, we have something called the product rule, where it says the square root of two things that's multiplied together is the same as the square root of them individually and then multiplied together, like this. If we have the square root, if you have two numbers multiplied, that's the same as the square root of each one being multiplied together. Now, in algebra, we often don't write the multiplication sign. We just stick two things together, and whenever two things are together for no reason like that, that means they're being multiplied. Now, this is identical to the rule we learned in the last section, where we said something about a to the power bn, ab to the power n is equal to an and bn. Okay, well, anyway, This parentheses is not necessary, but I have it there and I don't want to bother erasing it. So, but anyway, so that this is identical situation, okay, where you can split things up and the radical will apply to each one, just like the power applies to each one in the power rule in the previous section. And having said that, let's look at example 2, which is what happens is that you're going to solve a problem like example 2, let's look at, say, part A, 300. What you're going to do is split up 300 into 2 parts. 300 becomes 3 and 100. The square root of 100 is easy to do. That's just 10. The square root of 3, we can't do it without a calculator, so we'll keep it that way. That is, in this section, we're only going to do something called simplify, which means we won't bother using the calculator. Okay, we'll just leave it the way it is. So in the example 2, then, the square root of 100 times becomes square root of 100 times square root of 3, and the square root of 100 simplifies to just 10. So you have just square root of 3 times 10, and that's a good enough answer. But we normally write the 10 in front of the square root. It's just a tradition, okay, when the answer looks like that. And part B is the same way. So please do example 2 as part of your homework. And then next, example 3 is doing things opposite way. If you have 2 square roots and then you multiply together like this, you start here, well then you end up being here. So you multiply them on the inside and hope that something nice comes out, which it does in example 3. So please do that as part of your homework. And then the next thing we're going to look at, we're now on page 42, where we have the quotient rule. The quotient rule then is looks something like this, which is similar to this concept. That is, if you have the radical sign, the square root sign that goes over the whole deal, that is the same as going over each chunk. Okay, that is, it works out very nicely. And this is the same as the principle we learned in the previous section, which says an over bn. No, I got it backwards. Whatever. It's equal to ab to the power n. That is the exponent. If you can take it out to apply to each one individually if it is being applied to the whole thing. See, this is the identical thing that we learned from the last section. So with that, please do example 4, okay, as part of your homework, and example 5, which things are starting to look more complicated. Now, if things are looking more complicated, that changes nothing, okay? We're just going to do it the same way. For example, let's look at example 5. We have a big complicated thing on top, 2, 3, 4, x, 11, y, right? And then a complicated thing on the bottom, which is something about 26, and then x, 7y. Now we're going to first apply this theorem because there's a bunch of stuff in here we want to cancel out, and if we could. Now this relationship right here allows us to cancel things out. So what we're going to do is write everything in a giant radical, that is square root sign, and then 2, 3, 4, that's x 11, y, and then divide by 26, and then x 7y. Now, so then we end up with, see, we have 11, okay, and 7. So what we have on top is left is x to the power 4th, and well, don't forget the radical sign, right? And then 2, 3, 4 divided by 26 is 9. How do I know that? Because your book says so, and I don't want to bother. You can just punch it into the calculator, and then this, and then what's down here? Nothing. Nothing means 1, okay? In fractions, nothing does not mean 0. So we do this, and then that the 1 is just 1. Square root of 1 is still 1, so we put the square root back, and that becomes square root of 9x to the power 4th. Take the square root of each chunk of these things, that becomes 3x squared. And remember, in the radical sign, we're only referring to the positive root, okay? If we want to talk about the negative root, then we will put, let's say we have a 5, the negative root, we'll put a negative sign in front. That way there's no confusion. So that's how you would do example 5. And you use some of the tricks in this section. We use some of the things that we learned in the previous section in terms of handling this stuff, which is right here. Okay, and also what we learned in this section in order to handle problems of this kind. So please do the example 5 yourself. Even though I've done it here, please don't hesitate to do it again. And after you watch the video, and what you do with the examples is you look at the problem, you don't look at the answer, you just do it yourself, see if you can get it without looking at it. And then when you're done, then you can compare your own answer to what the book did and see if you got it right. So let's go to the next page. Okay, now we are at page 43, where we have, we're going to do some addition and subtraction. All right, now to do addition and subtraction, the trick to do it is that we're going to make things look similar. Because, for example, when you have two things, okay, if you have square root of, say, 3 plus square root of 5, there's nothing to do, okay? They are two different bases, and you can't add them up, because that's like saying adding a plus b. You can't add a plus b. However, you can add sometimes if you can turn b, make b look like a. Something like that, or a looks like b. As an example, let's look at example 6, okay, to see what I mean by that. For example, let's say your problem is example 6, okay, on page, is this 43? Yes, on page 43, where we have 5 square root of 5 square root of 12 plus 2 square root of 3. Okay, now the 12 and 3 are different, so you can't add them up directly. However, what you can do is in some cases, such as in this case, is you can simplify this to see if there's some similarity between them that you can manipulate. That is, you seek the weakness and destroy. Okay, we're doing a weakness, seek and destroy mission. So we'll see if there's a way in this thing. So we are going to factor this thing, so that would become 12 is 3 times 4, and 4, of course, is 2 squared. So that multiplied together to be 12. And then and that simplifies to that 2 being squared, we can take it out of the square root. That becomes 2 out here. So 2 times 5, it becomes 10. Okay, and once we take it out, and multiply to 5, so we end up being 10 square root of 3. Then you add up to 2 square root of 3 up here. Then suddenly we can add things, because now we're adding apples with apples, so to speak. So 10 apples plus 2 apples is 12 apples, because the square root of 3 at this point is no different than an apple, and that's all we care about it. Okay, and treat it like an apple. So please do example 6 as part of your homework. Next, let's look at example 7. Now, example 7 is more complicated, but the principle is the same way, as your book explains quite thoroughly. That is, we're going to break this thing up into chunks and see if there's anything in common between them. And if there is, then we'll be able to do the subtraction. And even though you end up being, the chunk might end up being quite complicated looking, but as long as they are the same, I mean, take a look, the chunks, okay? When you simplify the first part, it ends up being this thing, but it has ab squared and square root 2ac in it. And the other chunk end up with the same stuff, okay? ab squared, square root 2ac. Therefore, you can do the 120, well, what are we doing here? Subtraction? Yeah, then you can subtract and end up being 92 of the apple, okay? That big complicated thing, ab squared, square root 2ac, that's your apple. That whole thing is one apple. Okay, and then you just do the subtraction or something exactly the same way. So please do example 7 as part of your homework. The next story, we are going to do something that is done in algebra quite often. Okay, the so-called rationalizing. Well, that's just what it's called. I don't know what's so rational about it, but what happens is that we don't like square roots at the bottom of the expression, so we want to make the bottom square root sign, the radical, go away. The way to do it, let's look at example 8. The way you do it is, let's say you have square root of 3 over square root of 10. And how are we going to make the bottom square root go away? We are going to multiply it by the same thing, the square root of 10 on both top and bottom. Now in math, if you multiply by something that has a fraction that's the same top and bottom, that's the same as multiplying by 1, because that's what that is. That's just 1. Now, if you multiply anything by 1, you haven't changed anything, okay? Anything multiplied by 1 is still 1. So we can do this, and what happens then is that you multiply the bottom to bottom, that the 2 square roots of 10, you multiply together, that is just 10. Okay, because that's the meaning of square root, is when you multiply it by itself, it gets the number back. And then this thing multiplies to be whatever it is, we don't care. And let's say we write it down as square root 3, square root of 10, being that we can't simplify it or anything. But by now, that you have finished your task. That is, what we're doing here is remove the radical sign, the square root sign, from the bottom of the fraction, the denominator. And you think, well, there are purposes to do this. Back in the day when there were no calculators, okay, and dividing by a square root is extremely hard. So then that's why they came up with this trick of getting rid of square root, because now this division is quite a bit easier. Now you might think, well, but we have the calculator now, so why are we still doing this? Well, it's just a good trick to learn, okay, from the good old days. That way you appreciate how far we've come along in math, and we didn't have to imagine doing this stuff without a calculator. And people back in the day, they did it all the time. Okay, math wasn't near as much fun back then, in my opinion, when you have to do that. Ugh. Anyway, but we don't. Okay, so we are way advanced, and we are in a very comfortable, advanced society where we don't have to do that. But we still do this, okay, because this is easy to do, and we show that we are fully capable of doing what the people in the past can do. So let's look at the next page. And continuing, what is that? Okay, example 9. Now, example 9 is important, okay? Please pay attention to example 9 specifically. That is in this sense that we are supposed to do this. We have 4 over 1 plus square root of 5. Now, this trick that we're using in example 9 will be repeated in this course and the courses after you all the way through calculus. So please remember this trick. It's not a particularly difficult trick, but it's easy to forget if you didn't know that this trick is important, okay? And in fact, anytime you see a radical that's added to something, this is the first thing you think of to do. And that is, what you're going to do is do this. You're going to do something, the sign, you're going to change the sign in front of the radical to the other one, which is, if it's plus, you change it to minus. If it's minus, you change it to plus. And then you have, you write the same thing here, okay? Because being that they are the same, this is just multiplying by 1, and when you multiply by 1, nothing's different. So this is so this equation, this number is still the same thing. Now, at this point, what we're going to do is something, well, your book hasn't really mentioned this, all right. Yeah, so I'm just going to write this down. This is an extremely important equation that we will go into detail in the next section if you have forgotten about it. But here's the point, okay? A squared minus b squared equals a plus b times a minus b. Now, this is called difference of squares, and it's extremely important, okay? In algebra, trigonometry, calculus, well, basically anything you can think of. So please remember this thing, if you can. Now, or at least write it down in your cheat sheet, okay? This is probably the first thing you should write down. And then this is only important, but only when you see a radical, which doesn't happen that often, but does show up once in a while. So this is a trick that you want to use. Basically, anytime you see this situation, okay? So we're going to multiply this thing. So first, we're going to multiply the denominator, and we're going to follow this rule right here. which means that once you have the plus and minus, you end up being the square of each one. So we end up being square of 1, okay? And then minus the square of the second term. The square of second term is just 5 because it's the square root of 5. So we end up being 1 minus 5 on the bottom, and the top is whatever it is. We'll write that down here, but we can't do anything about that. So that is the answer, okay? Well, actually, in this case, the answer cancels out because you have a 4 in the fraction on top and the bottom, right? So then you can cancel out the 4, and then you have a negative sign. I should probably write that down. All right. So this equal to 4, 1 minus square root of 5. That part doesn't change, and then have a negative 4 on the bottom, which will be, if you cancel out the 4, okay, then we have minus 1 minus square root of 5. Now, the minus 1, we'll keep this in parentheses because the minus 1 down here translates to a negative sign over here. Now, this is very important. Don't forget this. And the negative sign over here translates to, you multiply by each one, okay? The negative is just negative. The negative sign will multiply by each one, so it becomes minus 1 plus square root of 5. And that's how your book come up with the answer. Now this part is, the point is, however, that this trick is what we're going to use. And it follows this formula. That is, you multiply each one, okay? And then you subtract it by the square root, which becomes squared, so you got rid of the square root, which is why we did this. So once you get rid of the square root, then you have, this is called, what is this called? Rationalize or something? Anyway, this is an important trick that we're gonna be using. So please focus on how this is done, and then and then we will apply it later, okay? Specifically in cases like this, where you have two square root things, just one square root thing plus a number, and you want to get rid of the square root from the bottom, and this is the standard trick to use to do this. So please do example 9 as part of your homework, and make sure you got this thing down in your list of formulas to remember. But you don't have to write down the Pythagoras theorem because you're supposed to know that. Okay, you should not ever have to look up the Pythagoras theorem. That's something that's the one theorem you need to know if you have studied any math at all. All right, and so that's that. And then the next thing, let's look at the bottom. We are now at page 45. Okay, so at the bottom of it, page 45, we have something called the principal nth root. Okay. I normally just call it the nth root. What that means is that we have the square root at the nth power of some number a. Now let's say, what does that mean? Well, it means, let's say we think of the number 27. Okay, say 27, let's pick the n to be 3. So n is normally a square root written like this means that n is equal to 2, like this one. Okay, you can write down, but nobody writes down 2 because the square root just means 2. But if you have the cubic root, then you will have to write it down to not confuse it with the square root. The cubic root, you have the power 3. What does that mean? It means that you need to think of 3 numbers. It says here, 3 of them. Okay, you need to think of 3 numbers that multiply themselves together that equals to 27. And what might that be? 3 numbers, 3 identical numbers. Okay, so 3 numbers multiply themselves to be 3. Then you think about it, and eventually you will come up with the answer. Obviously, that is well, this is not equal right now, but I'm just describing what this means. So there's 3 numbers that multiply themselves to be 3. Okay, it's gonna be equal to 27, and therefore the cubic root means that that is 3. That refers to the number which, if it multiplies itself by 3 times, will become 27. Is what this sentence means. Now let's consider a different case. Okay, let's consider the cubic root of 8. 3 numbers which multiply by themselves together, all 3 of them will become 8. That would be 2. And then let's say we think about something else. What about let's see. Let's consider the number 32. Okay, and then we take the 5th root of it. What that is, we need 5 numbers that multiply by themselves together. There's 5th. Okay, so imagine 5 numbers, 1, 2, 3, 4, 5, and when they all multiply together, they will equal to 32. And then so then it doesn't take you long to try. Let's try 1. Well, you can't try 1. 1 multiplied by themselves doesn't go anywhere, right? So let's try 2, and 2 multiplied by themselves 5 times, they will be equal to 32. So as a result, the 5th root of 32 will be equal to 2. And that's how you do all kinds of roots. The calculator does have a function, if you investigate it. I don't think we're going to go into that in this section. But the calculator does have a button where you can take whatever nth root you want, okay? Even if it's 100 or something. It just basically, you imagine breaking it into various chunks. But remember, this is not division, okay? This isn't 32 divided by 5. And in fact, it has nothing to do with division. It has something to do with imagining 5 numbers multiplied together, see it in your mind, 1, 2, 3, 4, 5, identical things. And they have to multiply together to reach 32, whatever that number might be. And most of the time is not such a clean number. So like, wait, what is the 5th root of 33? I don't know, you just need it's 2 point something, okay, a little bit more than 2. So you just have to use a calculator and then it will tell you. And so with that, please do example 10 as part of your homework. Okay, and then finally we have at page 46, we have something that matters quite significantly. Well, is that the radical root that we just learned is also written as a fraction. That is, the cubic root of, say, n, okay, is also written as a to the power 1 over n. Where are we? 46. Okay, so that is the whole point. What that means is that let me clean up the board. All right, now let's look at page 46, where we have this particular notation. That is, the square root of the nth root of a is can also be written as 1 over n of a. You write it as a fraction. The idea is just that sometimes this is easier than drawing the radical sign. So they are exactly the same thing. Now, in the last section, we have learned this part. That is, a to the power p and then raised to the power q is the same as a to the power pq. That is, you can, in this situation, you can multiply the exponents together. So you get this. As a result, being that a to the power n, the nth root is a fraction, if you then raise it to the power n, m, that's the same as multiplying the fraction 1 over n with the number m. Okay, that is that's what this thing means. Whenever you see a fraction, it means this. And also, or if you say it another way, is if you are raising to a to the m first and then take the root, so then you have a to the m and then divided by the n is exactly the same thing. So either one, the point is that when you are doing the nth root, you are doing the division. When you're doing the regular power, then that's the number in the numerator of your exponent, where your exponent now becomes a fraction. Okay, now that is the best way to feel familiar with this type of thing is by doing practice in your homework. So look at the example on look at the example at the bottom of the page where you have a quick sample. Okay, let's look at it. So you have a number which has raised to the power 2/3. How do we do that? Well, the bottom number 3 means you have to take the cubic root of 343. And the top number means after you take the cubic root, you better square it. What is the cubic root of 343? I guess it's 7. Okay, 7 times 7 times 7, 3 times. Imagine 3 7s multiplied together. That is 343 if you do it on the calculator, which I'm not going to bother right now. So then once you figure out what the cubic root is, then you raise it to the power to 2 times, which is 7 times 7, and that becomes 49, and that is your answer. So please do example 11 as part of your homework. And next, let's look at example 12. Yeah, example 12 is a similar deal. And then example 13, the same thing. Okay, they have a negative value. Let me see. Now let's look at example 13, where we have a situation where something is being raised to a negative value. First, let's ask ourselves what happens when anything is raised to a negative value. That is a to the power negative n. That is always, I think from the previous section we have mentioned this. If not, I'm mentioning it now. Okay, the negative value always means that it's in the denominator. Okay, so all you do is see the negative value and knock it below the division line, and then now it's positive again. This is exactly the same thing. It's another way of writing it. So then let's look at example 13 part B, where you're supposed to calculate, say, 16 over 9, okay, to the power of minus 1/2. And how we're going to do that? Then we are going to do it like this. Being that it's a fraction, I mean it's a negative value, like I said, you got to push this thing below the division line. So it becomes 16 over 9, like this, okay? And then now it becomes 1/2. Now 1/2, as you might remember, 1/2 is the square root of 2. Okay, so then we're going to take the square root of this thing. So that would be equal to, keep the division line there. So that will be equal to, becomes 4. Okay, the square root of 16 is 4, and the square root of 9 is 3. So at this point, now what? I haven't mentioned this, but let me show you the cheat sheet. Now remember the algebra properties page that I showed you some in the previous video. These properties, they're very important, and one of them is something that I showed you earlier today, where the factoring where x squared minus a squared is x plus a times x minus a. Now, as I have written here. Now another thing we should look at, in fact, your book might have something like this in somewhere, in some page, but I haven't looked. So, but either way, you should make this thing yourself if you don't have one, because it's better if you make it yourself, because then it's customized. Now I'm talking about this thing, okay? Arithmetic operation principles, and very important is all the fraction manipulation. How do you do fractions? Now this is of particular importance. It's what to do when you're dividing by a fraction, which is what we're doing right now. See? We have a fraction in the denominator. The question is, now what? Okay, why there's so many lines? Now notice that this is the main fractional line. This is just what's down there that happens to have a fraction in it. So this line is shorter. Now how do we handle this? Now look at this rule right here, okay? When you have something dividing by a fraction, the trick is called invert and multiply. You notice that it flipped B and C around upside down, so now C is on top, and then that's your answer. So what we're gonna do is the inverse and multiply trick. So we'll flip this around, and so the answer is 3 over 4, and that is being that there's just a 1 there, so we don't have to do anything. So that's your answer. And this is very important, okay? Please focus. Please take a good look at this page and write down whichever one that doesn't look familiar to you. All these fraction rules, because frankly, my students, even up to calculus, gets confused by fractions. Why? Because they don't have these rules. So please take a screenshot of this or find it somewhere else, doesn't matter. But remember all the rules in here, especially this one. This one is the most confusing, okay? People get lost all the time. And also this one too. What do you do when you have a fraction in the numerator or the denominator? And so on. All right. So, but I will go more into detail on this stuff, I don't know, at some point, okay, before the end of this chapter. But right now, let's move on. So for homework, please do all the examples in this section from 1 to 13, I believe, and then make sure you know how to do each one. And as the book gives a thorough explanation, well, most of the time, and as to how to do it. And try to make sure that you know how to do every single thing thoroughly, okay? For homework, it's the same ones that I showed you in the beginning of the video, but I have also typed out under this video in the video description, which is on page 49, problems 13, 19, 25, 29, 31, 33, 41, 45, 51, 55, 59, 63, 67, 69, and 73. Now, all that sounds like quite a bit of homework, and it might take you a while, but it's very important to do them and try to get as fast at doing them as possible, fast and, of course, accurate, okay? That if you know how it's done, then you will be pretty accurate. Once in a while, you may make a mistake and got confused and thought, oh, what was 2 squared? Was it 5? Or 1 times 1 equals to 2. I've made those mistakes, and it's okay. But the point is that when you see the right answer, you will immediately know, oh yeah, right, 1 times 1 is just 1, it's not 2, and that sort of thing. But you do want to be as good at this stuff as possible. So if doing all that homework that I assigned isn't quite good enough, and you feel like you need a little more practice, then pick a few more problems until you feel good at it. But after you have given it a solid try, then it's if you feel like I'm just still not as good as I imagine somebody might be, that's okay, okay? And once you've done enough, it's time to move on to the next section.